Excellent point. No, he's proving himself better than you, Noah. He's setting his talk ahead of time.
All right. Let me know.
Just give me a few minutes, Ron. Download it.
Did you tell it to the 9?
Tall? What's tall?
Should have been right in the room,
Ray Troy's talk.
Yeah, that's right. If it was on Ring Boom, everything. Is that your product placement scheme? You should be in front of the camera for that.
Yeah. All right,
if you'd gone to the police first, none of this would have ever happened.
Shall we go?
Give me a second. I got to pull your talk up. If you'd send it to me ahead of time.
I know. I'll forget to send you the other one ahead of time too, just to be consistent.
No, exactly.
Just brief.
What the hell, Ron?
Are we
What?
still setting up
You
video?
formatted it letter.
Don't even ask about that problem. There's some weird problem with PDF LaTeX in it. This version of the
Yeah, it's clearly a superior way to do slides.
Oh yeah.
You're quite right. Why didn't I think of that?
Are you ready?
I've got to resize everything.
Okay. Are you sure you got source them?
How long is this video? I'm sure.
54 seconds. All right, I'm going to run the video because it's sort of about Microsoft, but not really.
The only problem with Microsoft is they just have no taste. They have absolutely no taste. And what that means is, I don't mean it in a small way, I mean it in a big way. In the sense that
Testing.
they don't think of original ideas, and they don't bring much culture into their product. And you say, well, why is that important? Well, you know, proportionally spaced fonts come from typesetting and beautiful books. That's where one gets the idea. If it weren't for the Mac, they would never have any products. And so I guess I am saddened, not by Microsoft's success. I have no problem with their success. They've earned their success, for the most part. I have a problem with the fact that they just make really third-rate products.
So, anyway, I don't know what made me think of that when I was trying to compare how you do things in Linux, how you do things in plain Linux, but I'll let you guys figure it out. So,
Do we have any culture?
huh?
Do we have any culture in our product?
Well, you know, just the fact that they make things like this tracing thing work in Linux, but as you can see in the paper, it's pretty hideous. So what I thought I'd do, because I always like this kind of demo, is I would show sort of the system call tracing done as a couple of shell commands. Because I always feel like that if you can do it that way with something in Plan 9, you probably got it right. And if you can't, you probably got it wrong. So all I'm going to do here, you can see the command up there for echo hang greater than proc whatever control. So that's the standard way that you know, guarantee that something's going to sort of hang when you do the fork. So, you know, so I'm going to do that. And what it kind of means is that the next guy, well, maybe this guy's going to hang, so we're just going to kill it. Well, let's not kill it, because actually that's okay. So what I did is it looks like the hang was sticky from the first time I did it. So anytime that RC does essentially a fork exec, then it stops. And what it stopped is the echo command, which is going to make it stop, which is kind of cool. And so now, you know, I say like, let's find out what the pit of echo is. Oh wow! Now is a bug in the whole thing. Can't let them all.
Skip to a window, God.
Okay. So we're gonna let that reboot, and I'll do the rest of it. Nothing's perfect.
You know, Jim's laughing at me somewhere right now. He actually
Oh, I
used
know.
live stream.
He's not watching this, I think.
Oh, he's got a Windows box.
Now I'm grabbing Eric's IP address, so the streaming is going to end right now. So, you know, it's all about serve and protect, really. So anyway, so this is about system call tracing.
Great job, Ron.
So what this is about is if you run Lex and you get the Beamer class, and then you actually build a file with it, and you discover that it's occupying this much of the paper, they say, oh yeah, we can fix that. You just remove all the beam refiners and reinstall them. And the problem is you have to find them first, and I haven't found them yet. So it's somewhere deep in the bowels of the PDF Tech install tree. So, you know, why bother? And then, you know, some examples of, well, why you care. And, you know, the general problem I have, and I think the other people maybe have it less than I do, and others have it more, but, you know, something doesn't work and why. And where this began with me was a long time ago in Blue Gene when things were just going belly up on me. And I needed a way to do system call trace, but then I keep finding a use for this. We actually found a use for it today. We traced CS and use CS query to watch what CS did, and that can be fascinating. But, you know, you want to find out what something's doing and it's broken and you can't figure it out because there's an R fork in the picture somewhere. How many people use ACID with trust? I'm curious. Okay. So, you know, it's always interesting when you see it run a line and there's an R fork and the process disappears, and after that, it's a pain in the neck. So, you know, but the fun one, just last summer, for 9VMs, what I do is I have a Bitbucket tree where I take the sources from sys and I commit them to the Bitbucket tree. Then I check it out and I do a full build and install of all the binaries for 9VX. And then I just run things to see if they work. It's just a nice way for me to convince myself I can do a full build from source. And I like using Mercurial because then I can just go to the web page and look for diffs and try and see what's going on. But post July 2012, 10 build, date just wouldn't do anything when you hit date. Just type date, just sit there. Nothing had happened. And then I get man and hit return and it worked fine. Give me the date, everything was fine. So that was a non-obvious failure. And more interesting is Acme, you start up Acme and working and exit Acme and like half the processes would just still be sitting there doing nothing. And you look at them, they're all stuck on a P read from standard in. So things were really bad. And here's a trace from, we don't have a laser pointer, do we?
No, stand on the chair.
Yes.
Is that why I know I did that?
You were paying attention during his talk because you were starting to
I was asleep. No, I was huh?
What's wrong with your mouse?
Oh, gee, this is more fun.
Corey, you and your logic.
So the standard, that's one reason. So the standard format for the output from this thing, there's the PID, the command name, the system call name, the PC, and then a set of args. And there was a lot of discussion between Gorko and Nima and some other guys and me about how to format this because we weren't clear on it from the first. But
This is not the slides you sent me.
oh. Things are tough all over. So it should be the slides.
This one's not in the...
Okay. Oh, well, okay, just photograph the screen. So those people should have come here. So here's the address of the string. And the nice thing there is you can see it's an on-stack thing. On-stack versus on-heap. So it's actually nice to know the address of the string. And then, of course, you always want to know what's in the string. The number of bytes and then the offset. And then here's the return value 1. There's, you know, nothing there. And then this is the part that is actually kind of handy. This is the 64-bit timestamp. And the way the 64-bit timestamp is, it's essentially right after we start, from having stopped to let you read this information to right before we might stop again. So these times, those times are times for the system call and nothing else. You're not seeing any overhead from the fact that we're actually tracing the program, which is pretty important. But look at the problem here. Dave just started up and did a read from that guy, which is FD0, which is standard in, which is probably a bad idea. It doesn't make any sense, okay? And then the date, it returned with a 1. This is me getting impatient, hitting return, and I read a new line, so that makes sense. And then it said, oh, that's weird. You know, I guess I'll close FD0. Well, for a lot of programs, that may not also be what you wanted either, just to sort of randomly close FD0 for no reason. And Dave has no business or no need to close FD0, so what's going on? And then from this point forward, it's actually kind of normal, right? We do an open on dev bin time, and that returns FD0 because we just closed FD0, so, you know, just overlay standard in with bin time. So, you know, very quickly, you kind of sort of say, what the hell is going on? And so maybe it's worth looking at the source, which is always fun. And here is sort of the post-July source. for what happens when you do NSEC. And there's some stuff in here that was news to me. One of the things is this sort of array of FDs. And then down here is this new comment, which is that threaded programs may have multiple procs with different FD tables, so you need to open dev bin time on a per PID basis. Okay, that sounds good. And then we do this PID equal toss arrow PID. This is very good because it means we're not doing open, read, close stuff anymore. And then we kind of look, and if you look, we're kind of looking for, gosh, have we been here before? Well, we'll use the FD we got. Otherwise, you know, we'll do some other things. But the key thing here is there's sort of this fall-through case, which is here. If FD is divided by PID equal PID, you know, and if you kind of look at the code for a bit, you realize, this thing actually thinks that we've been here before, and it's doing a P read, and since we haven't been here before, it's doing a P read on FD0. So this is kind of pretty clearly what has gone on. And the question is, you know, why does it think we've been here before? Well, you know, it's checking for you know, that PID equal, you know, FD divided by PID. Well, how could that happen? Well, it could be if my get PID is 0. Well, how could my get PID be 0? And you walk your way back and you realize that this toss struct is something really messed up on it. And this is where it turned out that this was a 64-bit 9VX, and we were running a 32-bit kernel, so essentially we had a heterogeneous case. And the unstruct toss struct was wrong. The size was wrong. Okay, but the point is, this and the Acme bug and your other bugs were, at some point, all they will do is point at them and go gug, because I have no idea what's going on. Whereas the ray trace really gave me a place to zero in on very quickly and figure out what might be happening. First the read of 0 to close, and then opening dead bin time kind of tells you that there's something going on with bin time, and then you can take it from there. So it really helped me a lot, and that was actually a fairly simple case of kind of finding out bad things. And then you know, there are other things that kind of break. So you know, when I was doing this paper, I had this problem with trough, and you know, so we do this trough, and then we get a post node right on a closed pipe. It's like, what the, you know, why would you be writing a closed pipe? And you know, what do? Well, actually, it's a shell pipeline, and you know, this is a little hard to follow, but basically what's going on here is you do a ray trace -c, and then you know the bin rc -c, and then you just trace this thing. Then at some point it runs for a while, and here's an exec, and here's bin gs, and here's -1. Okay. So the exec on bin gs failed. The problem wasn't you were writing a broken pipe. The problem was that bin gs wasn't there. Now the reason for that, to get back to another problem I had, the make on bin gs was failing, and that's when we got back to when somebody changed the stack on 9VX to be too small. So this was the initial approximate cause of the problem, but the real cause of the problem was the make was failing because somebody basically made the stack too small, and I found that problem again with ray trace. And they're just these things that aren't obvious. Part of the reason is that, you know, whoever looked for this error, well, actually the child looked for the exec there, but the parent didn't. The parent just assumed everything was working. So there are just things you can find that are kind of fun to watch. And the other thing is that, you know, people have told me, well, you know, you can just use ACID and LTrust, but, you know, there are 3 machines that I use a lot that LTrust didn't work on that I cared about. And, you know, there's a lot of stuff that comes with ACID, so sure, I could maybe got that to work on ARM, but we're building these RAM disks. The RAM disks should be small, and at some point you run out of the number of files you can put in. So, you know, I don't want to put all those local files on the RAM disk, but even had local files, ACID just isn't fun to do tracing with work in my experience. You know, maybe an easier way to do it, but I just don't find it as convenient as this rat race program. So, how's this thing work? Well, to make this good, there's a couple of pieces you need. We're gonna ask the kernel what the system call was that the process just did, and so actually we need the kernel to stop the process when it does a system call, so that we can ask it what's going on. So we need to tell the program to stop on system call entry. Well, it turns out that was in every kernel I looked at. I had never noticed it, but it was there. So that was actually fairly straightforward because we didn't have to do anything. We needed to print the system call args, and actually 9VX already had something that sort of did that. In fact, to this day, if you invoke 9VX, I think it's -G, it'll print out every system call that every process does. So actually most of the work was already done for me by the time I got there. Thank you, Russ. And so the real thing that had to be changed is, 9VX is printing it for every guide to the console, which is not what we really wanted. And so what had to happen is we needed to basically find a way to scarf that print string away until somebody could read it. So I'll show you how I've done it in a minute. And well, a lot of this, where this really began is to take the 9VX stuff and kind of generalize it and make it a little more useful than it was. So the 9VX printing was really raw, and then of course you have to extend, the proc device. So there's a new proc struct that changed. One thing got added. There's new code in syscall. I'm just going to walk through some of this code to give you an idea of how simple this was to do. Some dev proc, port stuff. So let me quick walk through this. I figured this is a little experiment I'm doing on you people, which is that I figure it's a workshop. So I was hoping people wouldn't be too scared to look at some code. And there's this bug in 9VX now on Mac OS where you change things behind the window and it doesn't work right anymore. Is that it?
Hide and restore, yeah.
Okay.
But just keep it in a frame so I can teach people motion sickness on the net.
At least you can't throw up.
Sure.
Clearly you haven't been to chapter.com.
So if you, I'm sorry, this is the only problem with doing this sort of thing live is that,
Now we can see how Ron can't type.
yeah.
No, it's not on top.
So, all right, can't find it. Basically, what we added to the proc start is this thing, char star syscall trace. And basically, most of the time, it's not pointing at anything at all, because most of the time, the processes are running and they're essentially empty. And then, let me just show you for the Kirkwood and the PC. So I don't know how many people have looked at this. This is the syscall function up here. And, you look at a few things. And then you basically, pretty much right here, this is actually, believe it or not, the most important pieces of this aren't really new. So this thing, proc control equal proc trace syscall, look in your old kernel now, it's there, okay? And so all you really want to do, you need to validate that the SP that you pulled out of the URIGs is good. So, if that thing is in the top page of stack, which is sort of guaranteed to be valid, then you don't bother, otherwise you do a valid adder on SP, and you make sure that the maximum number of args longs are kind of okay. Okay, and as they are, we call this thing called syscall format with the system call number, the PC, and then you sort of cast the stack pointer to a VA list. Now, here's kind of part of the trick. You set proc control or proc stop me, then you do the proc control. And what really happens here is here's where you go away for a while. Other things run. Okay? And when the neatest part about this, so when we come back from here, if you haven't read that syscall trace thing via the proc driver, it's going to be gone. You set it to nil. But the fun part about here is when you come back, you need not still be being traced. So you're stopped, and the guy tracing you can make an option to sort of let you go. That's kind of nice. But you can't actually easily do that on some of the things that have syscall trace. And to give you an idea of sort of how common this stuff can be, yeah, let's hope I can find it now. Wow, this window's small. Because you can see it's just a very small number of lines of code. There it is. Sorry. So here's syscall, and gee, this stuff looks really, really similar. In fact, it's close to being identical, but you know, there's a few things different between, say, the Kirkwood and you know, the PC. So there's just like a few words that are spelled differently, and that's about it. And that's the architecture-dependent part of this thing. Now, when I first did it on 9VX, if you look at the 9VX code, it's all in the architecture-dependent part. And when Jim McKee looked at it, he kind of said, well, you know, this you don't really need to do it this way. And you know, he had a few key, you know, important ideas. One of them was to sort of cast that thing to a VA list. And that essentially is what allows you to drop over into port. And you know, that code again is similarly pretty darn simple. Let's just quick look at that. So here's this thing called syscall format. It takes a system call number, a PC, and a VA list. And you know, this is the beauty again of Plan 9. What are we talking about? Like 40 system calls or something, okay? This is a major hassle in something like Linux where we're upside of 300 system calls now. Imagine just pacing out on all that junk and printing it all. That's one reason that strace on Linux is 100,000 lines. Okay, it's just gigantic. So you know, you do a few simple things that are always the same. You know, you print up arrow pig, you print up arrow text, because that's the name of things. You print the system call number, and this is sort of for the process private system call stuff. You might be out of range, so you just print that, and otherwise you print you know, the name of the system call. And then you know, this stuff is easy. So let's just take a look. Here's remove. You know, it's a very straightforward thing. You get a char star A, you print that in the user string, you know, done. So this turns out to be almost an unbelievably easy thing to write. One of the hardest ones is exec, because you've got a variable number of arguments, and you've got to kind of walk through this thing and print it. And I went ahead and did this arbitrary thing where I said, well, I don't actually know if there's an arbitrary limit on exec printing, but you know, there was. So that what I like about this is, that's all the stuff to print all the Plan 9 system calls, right there. Yeah. What?
Quite a few of them are deprecated.
You know, I left them in because I think.
No. So.
You're right.
There are fewer than you want.
Yes, there are. You're absolutely right. There are a number of these things that I thought maybe we ought to leave in, but we don't need, because they are deprecated. So that's kind of all of this change, and it actually is. The neatest thing about it is it was so easy to do. And that's why I played the Steve Jobs thing, is because, you know, Jobs pointed out taste applies to more than just Windows. You get the interface right, and you can do things like this. Now, you know, what's interesting, if you really look at, if you trace strace on Linux, for example, it is really an interesting thing to watch because...
Pull up instruments and shit on the Mac.
Huh? What's this?
Pull up instruments and shit trace on the Mac.
Oh, God, I don't know. The interesting thing about the Mac, I don't know if anyone's used dtrace on a Mac. You have to run it as root. So they have a thing called dtrust, which is like strace, except you can't run it unless you're root. So if you're trying to catch a privilege problem, you can't, because there's no privilege problems when you run it under trace.
That's correct.
That's correct. There's no privilege problems.
You're right.
But no, you can do is that you can tell a pig.
You can?
Yeah.
You mean you, I think?
We did the Mac
No,
seminars.
you can tell.
Oh, that's true. That's true. But the naive user who's used to tracing on every other operating system wants to play it off.
I agree it sucks.
Yeah. So the thing about, and this gets back to interface design, I think that's really, you know, this thing itself actually isn't that important. The important thing is, you know, the way things work through on Plan 9 because of this textual interface and all this other stuff. If you look at strace, there's a minimum of 10 system calls per trace system call. And what are they doing? They're grabbing out stuff like the PC so that they can go back and hunt down, you know, what might be happening. And they've got to grab out stuff like args so they can interpret the args. Well, the kernel could have done that for you. But ptrace is a word aligned, you know, I mean, word at a time, pull data out type system call. And you watch what it does, and it's just hideous. So yeah, you know, I don't think anyone can really criticize the original ptrace design. It was a long time ago. That was 4 years ago. We might be a little critical of the fact that 40 years later it's the same damn design, but you know, I guess that's up to whoever uses it. So, you know, if you can actually do this, you know, S-trace bin date and S-trace S-trace bin date, so you can trace S-trace S-trace. And, you know, again, if I S-trace bin date, I get 71 system calls. Date is 71 system calls. So the other interesting thing there is we got into the discussion of shared libraries on Go mailing list. And, you know, I said something like, gee, I'm really glad that they went with now using shared libraries. And I got the usual tongue lashing from one of the Linux guys about how important it was to have shared libraries. Well, yeah, it is really important because out of the 71 system calls, I think 65 deal with the fact that we're using shared libraries. Okay, so we do all this stuff to get the date, but most of what we do isn't about the date at all. It's about setting up the shared libraries so that we can have return from libc attacks against us or something. You know, and you know, so then I did the S-trace of S-trace and did 1,770 system calls. And you really watch each one, and many of those things are just simply the fact that, I'm sorry, I was wrong, it's only 58,000 lines of code. You know, and what's it look like? It looks like this. Okay, so we do a wait, and then we do this sigmask, and we do this trace thing, and now we're looking at, what am I looking at? Well, I'm looking at the code segment, RAX, RDI, RSI, RDS. You know, I'm really digging down deep. And that's why we can have almost identical code for every architecture in Plan 9. But on this interface, you have to have different code for every architecture and every kernel, because the interface is wrong. So, you know, I think that's what's more interesting about this than just the thing itself. I have to announce a bug. I'm kind of ashamed to admit it. I thought this worked, but I can't rat race for some reason. So maybe somebody wants to fix that this afternoon. But that's kind of what it looks like when you say rat race bin date. You see things, you know, and then when you rat race, you just see almost the same things, except maybe 4 times as many of them, but not 24 times as many of them. So here's a stupid example. I'll time tracing it. I forget who, the first time I mentioned this on the mailing list, the first time somebody did anything to say it slows things down. It's true, it slows it down by an order of magnitude. But that's life. I mean, a lot of times you're not going to catch timing errors with this because it really adversely impacts the processes. It's just life.
There's an amount versus the call, so I think that's the main story.
Yeah, I think we could change that, but yeah, we could. I don't know, Eric. I think actually the main slowdown is the fact that we're calling the kernel a lot to learn things. I think that's more because we're context switching from the process to being, and I'm calling the kernel and there's format.
Well, that's not helping, of course, but now
Yeah.
it slows it all.
Well, yeah, I would want to
Someone would
actually.
fix the allocator.
Huh?
Only someone would fix the allocator.
Yeah. Someone thinks it out there. But anyway, this is sort of a time of WCRC bin star. You know, I've timed making a kernel, and yeah, clearly you're going to be in a lot of pain if you trace things. You're going to slow down a factor of 10. On the other hand, you might find your problems.
Well, will only solve your problems when you're slowed down by a factor of 10.
Yeah, well, it's either infinity or a factor of 10. So you have to take your pick. So the summary of this is the code is there. I'm glad to talk to anyone about it afterward. But I think it's so simple that I don't think anyone is going to be surprised by any of it. It's a very straightforward design, and it's straightforward because the interface, you know, the hinge between user mode and the kernel. You can think of it as a hinge. The hinge is in the right place. You know, it's not the peek and poke interface of ptrace. It's, you know, you say syscall trace, and then you cat the file or whatever, and you're done. And you can actually write an equivalent of strace with the shell script. That was the first version of rat race, was a shell script. So there's really not a lot to that. And you know, it just gets back to the idea that these text interfaces are the right way to do this. Now, what I'm going to do, because it failed before, unless I'm out of time. Okay, I think I'm done. Any questions? Yeah.
Have you pushed this one? I can't. No, seriously.
No. Honestly, okay. I had 4 years ago, I implemented broke for Linux, and I implemented textual files in proc. like FP regs and regs and stuff. And we talked to some of the Linux guys about it, and there's just no interest at all. So, clearly, I'm not going to care about
Did
trying to
you
push this Linux.
consider using a queue between, to buffer the system call messages, to decouple printing from the running?
No, because see, the thing is, I think one of the most important aspects of this, which we're not exploiting at all, is that this can, in some sense, or at some level, be interactive. In other words, you can have a program that is invoking the system call trace capability, but between each thing is causing some other program to do something. And that something could be a lot of things. One of the things I have in my copy of rat race is a script called 2ACID. And essentially what happens is it's a way to connect rat race to ACID and have ACID do a stack every time, which is kind of nice. So I actually think that queuing it up for efficiency is not the issue. I think the issue actually is exploiting the fact that we really, in a very efficient way, get a lot of information about a process and could do things in between. And one of the things I think is interesting is the option of just saying, I've traced you enough, just go. Move on. Somebody should ask, are you going to fix the bug with the hang? Yeah, we'll fix that.
You could use ACID to sort through the system calls and break when you want to find the one.
Yes, and the other obvious thing is just extend ACID to use the rat break, the proc interface instead of saying breakpoints and all system calls. Why not? So ACID could use this instead of what it does now. It would probably be a lot less complicated. So again, unlike strace, you can do it as shell script, an awk script, C program, use ACID, whatever. There's many different ways to do this now, because again, the interface at the kernel level is right. I better stop because I think there's other people who have to talk, right? All right.
Ideally.
Anyway, it is in sources. Thank you, Jeff. Where's Jeff? Thank you, Jeff. It's in sources. I've tested it. It works great. So that's it. And with our regards to Steve Jobs.
No, so I'm all ready for it. So we can get it quick enough, so I don't have to stop it.
I didn't bring any way to display this yet.
Okay, well,
Do you want the laptop?
Sure.
Just get it.
I need a few minutes this time. It's one Eric or another.
you can tape it next time.
No, I didn't. I saved it.
It's actually
Well, I did wonder. I did wonder about that actually.